So this is missing slide, which I wanted to show. Most of the stuff is in this review. It's also available on archive, so you can download it for free. And there are many exercises. So, and as we go, I will be mentioning more and more exercises because I will be able to derive less and less on the blackboard. But let me finish this calculation. So I know I was a bit too fast. So because it highlights some subtleties. So let me just slowly repeat what I told you. So far, I can give you, if you want, hand-waving proof that if you start slowly and will accelerate the box, so we adiabatically turn on velocity if you want, then we will actually follow the ground state of a moving Hamiltonian. So to the first order in lambda dot, or lambda dot squared, if you remember, for diagonal for energy, first order perturbation theory actually gives you correction of the order of lambda dot squared, of perturbation squared. So I can say that my energy, E, it's a real physical energy. It's approximately ground state. It doesn't have to be ground state, by the way. I can consider any excited state. It's 0 m. M means moving. H psi m0. And then now we just use static perturbation theory. Once we went to a moving frame, we have a static problem. Nothing moves anymore. But we have an extra term in the Hamiltonian. So now I am assuming that x naught dot is constant, but it's not really important because if it's slowly changing, I can use time-dependent perturbation theory, and I will get static result anyway, just because x naught dot is slow function of time.
V of x minus x0 or just V of x?
Well, it again depends on which basis you use. It's V of x if you use moving basis. It's V of x minus x0 if you use lab basis. But if you add this term, you forget about the fact that basis actually changes in time.
But somehow now I want to find a fixed box, right? So my box
Yeah, but it's effectively fixed because you forget the fact that basis changes in time. So it's like, it's what I was saying, so you can expand in a moving basis. And then the fact that basis changes in time goes into this term. So even though basis changes in time, you kind of treat your equation of motion with partial derivative. You just ignore this fact that the basis changes in time. Or equivalently, you can say, I'll go to a static box, and then I just have to go back, just do unitary transformation. Now I had psi and psi tilde, they're related by u. But I want to solve time-dependent problem. So at the end, I can always, at the end, do unitary transformation. Yeah. OK. So, and then I'm using just perturbation theory. I need first order because, well, I can say that this is essentially psi. I have too many indices. OK, psi naught, let me use G just to highlight its ground state. H psi naught G. And as I said, ground state is arbitrary choice here. You can choose any state. So this is the leading order, and this is, of course, my EG. So this is my adiabatic theorem, if you want. Then I will get psi 1, which is this guy. H psi 1, psi 0, sorry. But this is 0 because psi 1 is orthogonal to psi 0, right? Remember first order perturbation theory. And H on psi 0, it's an eigenstate. So that's why first order drops. So I will get a contribution psi 1, psi 1. And I will also get a contribution psi 0, H psi 2, or psi G, H psi 2, whatever, plus psi 2, H psi 0. But you remember, projection of psi 2 to psi 0 is just minus sum of coefficients of psi 1 squared. It's just normalization. Anyway, so this will give me what I wrote. So, sorry, this will give me what I wrote. It will be psi 1, H psi 1, because H all n's are eigenstates of n, I will get sum of squares of these terms. So I will get x naught dot squared. I will get matrix elements of np0 squared. I'll get energy denominator squared, right? This is just coming from square of this term, and sum over n not equal to 0. But then, because I'm evaluating energy, I will also get En. But then from this term, I will get minus the same thing, but with E0. And it's easy to see. If I have expectation value of identity, it cannot possibly change. So if all Ens are equal to E0, I must get 0. So, but it's an easy calculation. And now I gave you an answer, but let me just say where it comes from. What is this guy? Well, I doesn't matter because I'm squaring absolute value. So I'll get h bar squared, then integral over dx 2 over L sine Pnx over L times derivative of Px over L. And this derivative with respect to x will be pi over L cosine pi x over L, right? So this is this matrix element squared, right? 2 over L, I remember my wave function square root of 2 over L times sine or cosine. Well, sine here, if I put 0 in the left boundary. Well, this is sine Px over L. It's even with respect to the middle, right? And cosine is odd. It's, sorry for this, but anyway, with respect to the middle, it's clear. The sine pi x over L is an even function. Cosine is odd. So it actually means that only even n's will contribute to the sum. So n is an even number. That's how I get this 4n squared in denominator, because it's En minus E0. Remember, En is proportional to n squared, but my n is even. So I can relabel n to 2n. So I get 4n squared minus 1. So I'll get 1 power from energy denominator. But then if I do this overlap, just plug it into Mathematica, evaluate, it's a fun exercise. Sine, cosine, you will also get like n, same says another power of this guy. And you also get n squared. Anyway, so, and then you can check dimensions work out right, because I got h bar squared from here. I will get also h bar squared. I can cancel it from here. So h bar squared will cancel. It's already, we see it's a classical result, which is a good sign. M will also, well, M will go to numerator because En is 1 over M. So, and there is nothing else dimension full. So I'll get mx naught dot squared times a number. And then you have to plug it into Mathematica and see that this number is 1/2. It's actually a fun exercise, and I'll give you another with dilations where the answer is actually more interesting. But before that, let me tell you how we can derive this classically. And this actually, in this case, it's sufficiently simple. You can still do it. But with dilations, it already will be much harder. And this gives you one of advantages of quantum mechanics compared to classical mechanics, because we have notion of stationary states. They're equivalent to time-averaged orbits. So classically, if we solve this time-dependent problem, at least normally, unless we deal with the adiabatic invariants, which are actually extremely complicated if we have more than one particle, we really have to solve dynamical problem. Just even when we go to a moving frame, still there is no like machinery of, say, static perturbation theory, or at least it's not really developed. So let me just illustrate how we can recover this result classically. So this is a simple problem. So I have a box and start moving it with acceleration. Instead of correction to energy, I will compute correction to the force due to the particle. And I assume there is a very fast particle inside. So it moves back and forth. Very fast means velocity of the particle is much faster than velocity of the box. And assume I start moving with acceleration. So now let me assume that this particle starts with some velocity little v in my box with some velocity capital V, which is x naught dot. And after some time, delta t1, my particle reaches this wall, right? And after that, it reflects, which means velocity v goes to velocity minus v. And this would be correct if the box was not moving. But because the box is moving, we know that we will get extra correction coming from the box, right? So little v goes to v minus 2 times velocity of the box. And velocity of the box will be, oh, sorry, it's not v, it's a delta t. I want to compute correction to the force, so I'm assuming that I'm accelerating. So capital V is a delta t. And I start at 0 velocity. You can, again, check. It's not important. Only acceleration is important. So now I can compute change in momentum of the particle. It will be minus mv plus 2 ma delta t1 minus mv, right? OK, this is the momentum change. Well, after this collision, particle moves back with this new velocity. And after time delta t2, it collides with the left part of the box and reflects, right? So now velocity of the particle goes from minus v plus 2a delta t1. So it was what it used to be, right? And then it goes, it changes its sign. But then it gets velocity twice velocity of the wall, but now it's 2a delta t1 plus delta t2, right? Because now my box is accelerating, and I'm assuming that acceleration is constant in time up to, and here where adiabaticity comes into play. So I'm moving very fast, so acceleration doesn't have time to change. So this will be high order effect. So my new velocity is v plus 2a delta t2. Now I can compute change of momentum, delta p2. It will be mv plus 2ma delta t2 plus mv minus 2ma. Oh, sorry, it's delta t2 plus delta t1. I apologize. Yeah, I don't know what happened to. Oh, no, it's OK. No, it's OK. OK. I already canceled. Yeah, sorry. 2m minus 2ma delta t1. Yeah.
This is delta p2 relative to p1 or relative to the initial?
No, it's relative to p1. It's a new change of momentum. Right, sorry. This is change of the momentum here, and this is change of the momentum here. So so total change of the momentum will be delta p1 plus delta p2. And total change in time will be delta t1 plus delta t2. And as we know that this is an average force, right? And now if we add delta p1 and delta p2, mv will cancel as it should, right? Where is that? Yeah. I have minus mv plus mv, so it's not important. Then delta t1 will also cancel. But delta t2 will be here. So I'll get 2ma delta t2 over delta t1 plus delta t2. And now I see where in classical language adiabaticity is important. If my particle is fast, then delta t2 is the same as delta t1. And then I will get ma. If particle is not very fast, I will get extra corrections. And this ma will, of course, lead to the same correction to energy, because we know that total energy is conserved, right? So if I apply extra force, I have to pay extra energy, and I integrate it ma, and I will get mv squared over 2. So we see where the same effect comes in classical language. So now let me consider this less trivial example of dilations. So here, I guess everyone knew the answer. I was just trying to convince you that using this machinery, we can recover it. And in the next example, I didn't know the answer. And so far, I didn't see a single person who knew the answer in advance, even though the problem is trivial. It looks like high school problem. So let's assume that I have a piston and say I have a spring. So I have a mass m here, and I have a particle inside. And I ask, what's the effective equations of motion if particle is fast? So you all know, of course, that this particle creates pressure. Because of that, there will be shifted equilibrium and so on. But you know, for equations of motion, it's not enough. Because if I study small oscillations, I need to know what is the mass. And it's intuitively clear that if I'm moving this wall, I'm also pushing particle back and forth. So I should get correction to the mass as well. OK. And it turns out, again, quantum mechanically, this is really a trivial problem. It's basically the same calculation as before. So we discussed that moving Hamiltonian now will be h naught, which is just p squared over 2m, minus L dot times d, my dilation operator, which is the same as p squared over 2m minus L dot xp plus px over 2L. So, and now I can do exactly same exercise as I just did on this. OK, I raised it already. Just say that I'm following actually if lambda L dot changes slowly. It actually doesn't have to be small. Instead of oscillations, I can say I'm just pushing the wall. But it changes slowly in the sense that quantum language, it means that particle doesn't have real transitions. We are not really exciting it. It's normal Landau-Zinner criterion of adiabaticity, if you want. If it moves slowly, I can use this as a perturbation. And my first order perturbation theory now will give me that delta E will be L dot squared over L squared. And then I will get sum over n not equal to 0, n xp plus px, well, I guess 4 squared over, well, now I think before I said it's not important what is the state of the particle. Now it's important. Now let me say that this particle is in state R. So it's a ground state, or could be some excited state. So now I sum over n not equal to R. And here I'll get n minus r. So before you can check, well, it's kind of obvious from Galilean invariance, but it's a non-trivial sum rule. So even if you consider n not equal to m, you'll get a totally different sum, but it will end up to be 1/2 always. So, and that's the same with this signs. It's a very simple calculation. But now you see all n, even and odd, will contribute. Or maybe only. No, only odd, I think, will contribute, right? Because now when I apply p, remember, I change even to odd. When I apply px, I actually keep even. So it actually means now different states will contribute. But apart from that, even matrix element of this is the same as matrix element of p. So you'll mathematically get the same expression, but even sum, not odd sum. So if you have your code for moving the box, then modifying code to squeezing the box takes really one line in Mathematica. So any guesses? This is correction to the energy. So it's L dot squared. Then dimensional argument is exactly the same. You just see that all h bars will cancel. So it has to be m by dimensions. I'll get 1/2 just for dimensionality. And any guesses? What should be here? Can you guess? So I'm asking, what's the correction to the mass of the piston, essentially, right? Because I will have kinetic energy of the piston, capital M L dot squared over 2. But now we are computing correction to the mass of the piston. So that's the expression for perturbation theory. By dimensional analysis, we see it's little m L dot squared over 2. But then there will be some coefficient, which is not 1, which is something else. Anyone would guess? Again, I guessed it wrong. I expected something. It was totally wrong, but then it made sense. Yeah, this was exactly my guess. And moreover, I can sort of even try to justify where this 1/2 comes from. because if you think about this, when you do dilations, you move only one boundary instead of two. And so you might think you have effect of one boundary and another boundary, perhaps interference, but interference never plays a role in classical limits. So it should be 1/2. One boundary should be exactly 1/2. And then we can say we get 1/2 from this boundary, 1/2 from this boundary, one together. It was really my expectation. I ran it and you evaluate it and the answer is different. Well, okay. It's impossible to guess. The answer is 1/3. And moreover, there is 1/2 pi r squared. And this is like a anomalous quantum correction. So now why I showed this example, it highlights something important. Mass actually is emergent quantity in general, which does depend here on your energy, on your temperature. Like we are not surprised that we have Casimir forces like pressure, which depends on temperature. This is not surprising. But mass is something, I don't know, comes from above. No, it's actually not true. But Galilean invariance, for some reason, maybe there are some deep reasons which I don't know, it's mass independent. Once we go to already dilations, we have a small correction. Moreover, if you do the same calculation from like relativistic gas of photons, you'll find same anomalous correction. It's kind of interesting. It's interesting that, well, this is a particle, but if you do calculation with photons, you will get, I don't want to discuss 2, but you will get 2 over c squared, and you will get E, and E will include Casimir energy. And amazingly, this comes from a totally different sum. It comes from a double sum. I tried to search any mathematical literature. It's absolutely not clear why that sum has to be related in any way to static sum. It's a double sum, so it's the sum which has a form like double sum n squared m squared over n squared minus m squared cube, something like that. So and why this sum is the same as sum over n, which gives you Casimir, I have no clue. I asked some people, no one knows. But it's interesting that Casimir energy comes here, and this is just a magic at this point. So I'm sure there are some deep relations, but I don't know them. So, and this 1/3 is kind of interesting. It shows that there is interference even in the classical limit. So, and that's kind of interesting. So it comes from the fact, so where this, physically, why interference doesn't play a role normally. It normally comes from the fact that in the classical limit, we deal with many states. And we have these big sums of n. And some are positive, some are negative. They all cancel each other. But here it's interesting. If you sort of analyze this sum, main contribution always comes, no matter what r is, from n is equal to r plus minus 1. So from nearby excitations. And there we cannot really, so oscillations don't cancel. There is a difference between n plus 1 and n minus 1. We have just two terms. But 1/3 has actually very interesting interpretation. So once you see the answer, you immediately recognize it. It's actually mass of a massive spring. If I say that I have a uniform spring with mass rho, right, and I am dilating it, now I know what kinetic energy is, right? It's some density which is, say, uniform times x dot squared over 2 dx, but x dot is equal to x over L times L dot, right? It's obvious. So particle in the boundary, or my density in the boundary doesn't move. Here it moves with velocity of L dot. Now, if you average this x dot squared, average of x squared is 1/3. So it's actually in the classical limit, this fast particle inside the box is just equivalent to a massive spring. So this analogy with spring, and this is so far, it's also amazing. And you can just, I'll probably talk about this later. It's not really related to this bags to be square or whatever. It's just related to dilation symmetry. So for example, if you take any conformal field theory, I don't know how to do calculations there, but you will get dilation mass 1/3 of translation mass plus quantum corrections. Because I will give this argument. So it's actually, in the classical limit, mass is related to just expectation value of this operator. And x squared is 1/3 from just dilation symmetry. You don't need to know anything, any details. OK. So now, if you want to challenge yourself, I urge you to do this calculation classically. And I have to say, I was, when some point when I knew about this result, I thought there should be a way to get it. So it's the same story. I change L. In time, I have fast particle inside, which moves some velocity, high velocity. And I want to compute, say, correction to the force due to acceleration. So this, say, starts moving with acceleration. And I was sitting on a plane from Europe, and I thought I have enough time. And I made it, but it took me 4 hours to do this. And the only way I could do it is because I knew the answer. It's not a hard calculation, but there are many subtleties. So like in Galilean case, it was not important where I start a particle. Here it is important, because you can imagine my box starts, my right wall starts moving. And if the particle is initially here, it will collide right away when the wall is still static. And when it completes the cycle, it will come back with exactly the same velocity as before. If I consider a particle which starts on this wall and moves in this direction, it will take the longest time before the collision. So it will have the largest change in the velocity. So now my change in energy will depend on position of the particle. And now I have to take this change in energy and average of a microcanonical ensemble. So once you realize that, you have to take into account that there are various corrections to time, velocity, and so on. If you do it, you will recover this 1/3. But at least in my opinion, this calculation is very subtle, very hard. Here, it's really one line. If you have well, you just need to evaluate these matrix elements for XP, but it's simple. Yeah.
So this is a Plaquet system, right?
It's not really important that it's periodic at this point.
Plaquet, I know that if I modulate this frequency omega, my eigenstates, I should start mixing states at E and E plus omega. So
yeah, but here I'm at the adiabatic limit. You see, I'm modulating much slower than this. No. But it's an opposite limit. It's actually, I have to do adiabatic approximation with respect to this particle, not with respect to the box. But I didn't try. I assume that, well, high frequency expansion will not, because here it's really how I move is not important, because I almost follow adiabatically. I'm not really exciting anything. So I didn't try it, but I think it should work. Well, it's kind of general. Okay, so yeah, and as an exercise, I derived this dilation operator classically. It's really simple calculation quantum mechanically. You can just say your psi n now. It's one of the ways to do it. Square root of n sine pi n x over L. You can now differentiate this with respect to L. And then you can observe, if you differentiate with respect to L with IH bar, d by dl, you should get, it should be A times pi n. And then you immediately recover that A is this. And moreover, I wrote it's xp plus px. You will get one contribution constant, which comes from differentiating this L. It takes care of symmetrization. And another contribution will come from differentiating with respect to L. But it's almost like differentiating with respect to x. And here, where you get px. Anyway, you can sort of do this exercise. It's straightforward. OK. Now, yeah, someone asked a general question. This is all nice and simple. But I'm at least personally interested in many-body systems. So how do we find gauge potential? So obviously, differentiating eigenstates is nice, but you don't know them, especially excited eigenstates. And even if you know them, they're horrible objects, so which are hard to differentiate to do anything. So we have to really find some simpler way of finding what this gauge potential is, and then building some approximation scheme. And this really, I'm not going into details, but this is where we really connect with Schrieffer-Wolff transformations, with renormalization group, flow equation methods, and so on. So I'll just write the equation which we need to solve. I use it for my purposes, but it's very likely you will see this equation in many places, a related equation. And I just said that, well, in general, we want to find a unitary which diagonalizes this Hamiltonian, right, such that this is diagonal matrix. And then we need to differentiate the unitary. But again, finding unitary is hard. It's as hard as finding eigenstate. So, and if you want, at least my way of thinking about it, and we can formulate the whole formalism of Hamiltonian dynamics quantum through unitaries. We can say we unitarily evolve just a state, and then I can say all quantum mechanics is just a unitary transformation, and I'm done. But it's hard to find unitaries. There are time-ordered exponents which are very complicated and so on. We prefer to deal with Hamiltonians, which are generators of these unitaries. So same reason here. We have any adiabatic transformation is a unitary. In general, it's very hard to find. So, and this gauge potential is an infinitesimal generator of this adiabatic transformation. So I'm going to translate this equation to something which I can differentiate. And then, obviously, what I'm going to do is I want to consider also u dagger at some lambda prime, which is lambda plus delta lambda, h, u of lambda plus delta lambda, right? And then I will get h tilde of lambda plus delta lambda. So this is always true, no matter what my unitary is. It's just definition of h tilde. But now what it means that my unitary diagonalizes h? Well, it actually means that both are diagonal matrices, and therefore they commute. Right? Because one thing we hopefully all know from linear algebra is that one diagonal matrix will always commute with another diagonal matrix. But if this is 0, I can differentiate this 0 with respect to lambda, and there is no harm. Right? And then what I see is that d lambda h tilde commutator h tilde must be equal to 0. Right? This is what defines unitary which diagonalizes h. But we already discussed what this is. We differentiated arbitrary operator, including h. So we will get u dagger d lambda hu plus I over h bar a tilde h tilde commutator is h tilde is equal to 0. So you see where this comes from. When I differentiate h tilde, first of all, I differentiate h, right? And this gives me this term, the first term. It's like d lambda h everything tilde. But then I will also get contributions from these two unitaries. And one will give me gauge potential with plus sign, and other with minus sign. And then I over h bar comes from conventions. And this has to commute with h tilde. But the nice thing with 0 that I can do almost anything with multiply 0 by almost anything, and I'll still get 0. So I can multiply it in particular by u on the left and u dagger on the right. Multiplying 0 by u and u dagger is not hurting me, right? So I'll still get 0 on the right-hand side. But here I will get rid of tildes. I will get this of this u. I will get of tildes everywhere, right? Multiplying by u on the left, dagger on the right removes all the tildes. And then I get equation which is very simple. And it has some name in mathematics, but I don't remember it. I heard it, but I forgot. But this is essentially equation for parallel transport. And as I learned quite recently, that's, at least if you remove the commutator and if you say just this whole thing is equal to 0, that's what people call the Wilson-Wagner flow equations. And that's exactly how one defines quantum integrability. And I will go through it. I don't know anything about integrability, understand me correctly. But it's kind of, if you know only this equation, you suddenly recover integrability. You don't need inverse scattering method, all these horrible constructions in classical physics, which maybe not horrible, beautiful, but complicated. So you will see that integrability comes from. Well, here there is also no time dependence. I'm trying to define gauge potential. So I'm just saying that in order, so formal definition of gauge potential, A, is IH bar U dagger, d lambda U times U dagger. But this doesn't really help me unless I know U. So instead, I can say, I don't really know what U is. I know what H is. So I need to solve this equation. Is it exactly or approximately or whatever, or try to find, that's how you find integrability. You can try to find H for each you can solve, right, explicitly the solution. And if you solve this equation, you know your generator of canonical transformations. You know your gauge potential.
So this is your way of mapping interacting particles to non-interacting?
Yes. So in particular, I hope I will have time to talk about this later. Our parameter lambda can be interaction. So far, I discussed trivial example, rotation or whatever. And then unitary U dresses non-interacting system to interacting. It makes problem from integrable to non-integrable. And this is generator. So you'll hear from Dima, like probably when he will talk about this integrals of motion tau z, which are connected in many body localization to these spins up and down. So if you can solve this equation approximately, then this will be generator of those guys. So this is really a generator for, if I consider weakly interacting fermions, I turn on interaction. This will be generator of my Fermi liquid quasiparticles and so on.
For the case of Planck-Hirsch modular bands, do you imply that this equation is exactly zero?
So it will be zero. So the truth is that this is equal to the following object. It's sum over n. It's an operator. D lambda En n n. So it's an operator which is diagonal. That's why I commute with it. And it's basically an operator consisting of generalized forces. So if you have a transformation which does not change a spectrum, it's like a symmetry or whatever, then this is zero. If you have a transformation which changes a spectrum, the solution of equation with zero does not exist. Because you can show that, well, you just can take expectation value of this operator in eigenstate of n. Sorry for being technical. This term drops because expectation value of commutator is zero. So you see that this is equal to just d lambda n. So it's basically identical to it if spectrum is invariant. If it changes, then you have extra terms. So now I can say why I used h bar so long. I could get rid of this from the beginning. Well, because now you can say, haha, but now I can say what it means to diagonalize classical Hamiltonian without referring to these unitaries, which we don't know what they are. And they might even not exist. So, and the diabatic invariants, which also don't exist for more than one particle, unless we have integrability. So I can say that classically, I need to solve this equation with Poisson bracket. If I can solve it, it means I can diagonalize classical Hamiltonian. And it means I can adiabatically generate, if you want, orbitals. Like if you still have a diabatic theorem in classical limit as a limiting case. You move slower and slower, and you can imagine there is some orbit, right? And this orbit transforms to another orbit. In non-integrable systems, the notion of an orbit is a bit tricky. So, but you transform one energy shell to another energy shell. And you can ask how you can do this transformation without exciting, without making energy shell wider. And if you can solve this equation, if you apply A, then it gives you transformations between different energy shells. So I will be returning to this equation more and more, well, at least occasionally. Let me also write an equivalent way of finding what the gauge potential is. And this will be equivalent to this equation, but I can write explicit form, and you will see where all the difficulties are. I can say, and let me assume in this talk that I have no degeneracies. If you have ground state with degeneracies, it's all interesting. As you'll see, these gauge potentials, they're related to geometry and so on. But I will ignore it here. So we know that A is essentially a derivative operator. But if I want to evaluate derivative, I can use normal perturbation theory, right? Because what is this derivative? It's infinitesimal change of my eigenstate if I change the parameter. So I can immediately say that m a lambda n is the same as I h bar m d lambda n. But by perturbation theory, it's nothing but m d lambda h n over en minus em. So in some sense, I told you it's complicated, but then I immediately wrote the answer what this gauge potential is for the matrix element. But of course, the problem is that if you have a friend experimentalist and you say, in the lab, you have to implement this term, you just need to find the operator which has this matrix element. So good luck. So advantage here that you can try some local ansatz and see what is the good local ansatz. So there, it's not really straightforward. And moreover, we can sort of use this trick, and we can see that in some sense finding gauge potential is equivalent to converting dynamical problem into static problem. So I can use the standard trick. I can use a Heisenberg representation. So I introduce this fictitious time. So I can say that this is nothing but integral from 0 to infinity. I call it tau. It's not imaginary time, it's just fictitious time. M, I'll get E h t d lambda h e to the minus I h t n. Let me put minus infinitesimal epsilon t for convergence. I understand it as a limit epsilon goes to 0. And then probably, I have to put h bar here. And I probably don't need this h bar anymore because you see the trick. So this acting on this will give me EMT. This will give me minus ENT. If I integrate this, I will get 1 over epsilon minus I over h bar, EM minus EN. And if I send epsilon to 0, if I didn't mess up, you will get correct exactly same answer up to a sign. So I will become I, h bar will become h bar, and so on. So in this actually, Chris Yerzinski in around 2000 got this expression, the classical limit. It has well-defined, it has well-defined classical limit because I see in the sense of if matrix element of this operator are the same as matrix element of this operator, integral, it's tau, not t. So then I see that my a lambda as an operator is nothing but integral from 0 to infinity dt times d lambda h of t. And here t means Heisenberg representation, not time dependence. Let me put it tau. It's a fictitious time with this convergence factor as usual. So, and you see where kind of difficulties are, because once you start evolving operator in Heisenberg picture, it becomes more and more complicated. I address it with a Hamiltonian. And then I have to integrate this monster. And this is what gives me solution of this equation. Yeah. Oh, it's a time for break. Yeah, it's actually a good time for break. I will come back to this equation, but I really want to highlight that it's highly non-trivial. So the fact that I can write an equation is not that I can solve it. But at least I can try to solve it approximately and so on. And I will sort of explain where all difficulties are later as we move on. So let me just briefly mention the last example. We can imagine now that we have some magnetic field and system of spins, say non-interacting spins. So it's our minus h cosine theta sum of, say, sigma I minus h sine theta sum over sigma xi. And now we can ask, what will be the correction to the kinetic energy if we change theta in time slowly? And now we will get correction to moment of inertia. So we got moment of inertia. So what we will get by exactly same arguments, that my delta E will be equal to theta dot squared over 2 times I, where I will be given this correction to the moving, to the moment of inertia will be given by exactly same expressions, but now I have to use angular momentum. So it will be a sum of all excited states, but if I'm in the ground state, I have only one excited state. So I will get generate of these rotations is sigma y. So I will get, say, the ground state. Say I can define moving frame that everything points up, right? So I can say it's up, or it could point left. It's exactly the same matrix element, sigma y down squared divided by delta. And I get 1/4 because remember my generator of rotations is sigma y over 2. Matrix element is 1, so I see immediately that my moment of inertia is n over 4. Well, it's h bar sigma y, so h bar squared over delta. N is number of spins. So I immediately in one line find the correction. So if I have some big object, rotator, which interacts with my spins, it will be dressed by spins, it will be heavier, and this is the correction to the moment of inertia. Moreover, you can see from here that if you consider finite, I consider only ground state, but you see ground state, excited state, it's not really important. So this matrix element is always the same, but this will change sign. Remember this energy difference between your initial state and final state. So if you're in the ground state, it's plus delta. If you're in excited state, it's minus delta. So at finite temperature, you'll have hyperbolic tangent of beta delta, right? Hyperbolic tangent comes because you have probability of B being down, whatever, e to the beta 1. Anyway, so it's Boltzmann distribution, right? Probability of up versus down is different by e to the minus beta delta. And it's kind of interesting observation, which is actually completely general, that mass has exactly, or correction to the mass has exactly the same sign as temperature. For particle, temperature is always, if we consider coupling to something equilibrium. So we can consider coupling to a mixture of up and down spins which satisfy Boltzmann distribution. So if temperature is bigger than 0, mass is positive, as it should. If temperature is negative, mass is negative. And then you just see that whatever you do is consistent with thermodynamics. Thermodynamics actually is always a queen of everything. Because if you can imagine that if you have a negative temperature, so you have mostly spins polarized up, you actually increase entropy by decreasing energy. And the system always wants to increase entropy, so you have to have negative mass. It's kind of interesting observation. And it's completely generic. OK, so now let me take a short break in this line of thought. So I will abandon dynamics completely. And I want to discuss, again, not much, but just to give you a flavor, connection of this stuff, this gauge potentials with geometry. So geometry will appears in many contexts. I will give some flavor. And some of the things I don't know well. But in particular, I'll discuss relation with information geometry. And that's where I make the link. And then later I will be mentioning when this geometry appears in dynamical response. Of course, we know very well Foucault pendulum. And you can kind of sort of see where the connections come from. Because the extra, this Coriolis force comes from this transformation to the rotation frame. And it's defined by this gauge potential. And as I will argue, gauge potential defines geometry. But also same with quantum Hall effect, same with like any people consider various topological insulators and so on. So this connection between dynamics and geometry is completely general. Yeah. But anyway, so let me define what I mean by geometry. So the simplest thing you know probably from geometry is Berry connection. And remember, it's defined as, well, now I will focus on quantum systems, mostly on ground state. So now I drop h bar. But whatever I define, if you multiply gauge potential by h bar, you will get something which is well defined in the classical limit. So you can define geometry in the classical limit in the same sense like Coriolis force or Cole conductivity. They're well defined in the classical limit. So, but I want to simplify notation. So this is Berry connection, and that's in the notes, I was trying to be more careful. I was trying to use curly A for this gauge potential and straight A for Berry connection. And I know here I was not very careful, but I'm not going to discuss Berry connection except for this particular instance. So everywhere in this lecture, straight A means curly A. But you remember Berry connection defines Berry phase. It's basically if I have an adiabatic transformation of a wave function, then if I find the expectation value, I will get the phase, and this phase is nothing but the integral over d theta, a theta. I assume that you know it, and I'm not spending time on this. If you don't, ask the question. I don't mind going through this. And this is really the phase. Moreover, you can just sort of see where it comes from immediately from this moving frame Hamiltonian. So remember, moving frame Hamiltonian is h minus lambda dot a lambda. Lambda could be theta. And then, you know, in the leading now, I want to solve Schrodinger equation. And I'm saying that, well, now, if I try to do time-dependent perturbation theory, this is my perturbation. I know in the leading order of perturbation theory, I'm just computing correction to the energy. And this is just expectation value of my perturbation. But this is exactly equal to lambda dot times expectation value of a lambda, right? My delta E, which is nothing, well, with minus sign. This is nothing but the Berry connection. Now, what is the phase? It's integral of delta E over time up to h bar. So I will get integral of lambda dot times a lambda d lambda. I can erase dot, and this is just, sorry, dt, I apologize, dt. I can erase lambda dot dt is the same as d lambda. So that's how I get Berry connection. So I assume that you all, or Berry phase, you all know it. It's just leading order of adiabatic perturbation theory. Anyway, now I don't want to talk about dynamics. I want to talk about geometry. And the key object, at least in this quantum information geometry, how it's called, or some people say just geometry, is a geometric tensor which was introduced in 1980 by Provost and Wally. So they even didn't consider eigenstates of the Hamiltonian. They said, let's assume that we have a family of states which are characterized by lambda. So in my talk, I will be talking about family of, say, ground states or adiabatically connected states. But in general, you can consider any other family. And suppose you change parameter lambda to lambda plus delta lambda. And you can ask, how fast my, say, ground state changes? So this defines a natural notion of distance between states. So, and I can define, following Provost and Wally, this norm squared. And there are various names to define it, but let me just define it as 1/2 as distance between wave function, psi of lambda minus psi of lambda plus delta. I'm just looking into difference between overlaps, or just consider, sorry, overlap of the difference. And 1/2 is just a convention. So I consider distance, I consider a state which is difference of psi of lambda plus delta lambda, and I look into its norm, overlap. So this is just definition. Obviously, if my psi doesn't change, nothing changes. But if it does change, I will get contribution. And this is the same as, you know, psi will give me 1. So this is the same as 1 minus overlap of psi of lambda plus delta lambda. If I didn't mess up, maybe I did. Anyway. Yeah, I have to square something. I think I need to square it. Anyway, so forget about this. I think there is a mistake here. Anyway, this is the correct definition. So want to consider overlap of psi of lambda plus delta. It's almost this object, but if I change psi by a phase factor, it shouldn't really affect the distance, right? So what they considered as a definition, so you have overlap of psi of lambda plus delta lambda, right? If psi doesn't change, this overlap is 1. So I subtract 1 from this, and I get something which is positive and characterizes how fast psi changes with respect to lambda. Moreover, this is a good definition of distance because in principle, at lambda plus delta lambda, I can multiply my psi by arbitrary phase factor, right? No one really told me. If I diagonalize Hamiltonian at some magnetic field, and then I diagonalize it at some different magnetic field, in general, you get totally different eigenstates, even if you don't have degeneracies. Why? Well, because you can just multiply each eigenstate by arbitrary phase factor. And this is not going, it's still a good eigenstate. Well, this definition takes care of this. So even if you multiply psi by a phase factor, it's not going to affect the norm. So then it means this is something which is probably difficult, probably physical. So now I leave it again to you as an exercise, but you can sort of see where it comes from. I can now expand psi of lambda plus delta lambda up to second order in delta lambda. In the first order, you will get 0, again, by standard perturbation theory. Our first excited state is always orthogonal to say, the ground state. I have to go to the second order. And if you go to the second order, what you will get, and now let me actually say that lambda is a vector parameter. I want to define a tensor. So it can be, say, multi-component magnetic field. So I can depend on either one parameter or more than one parameter. So what you will find is delta lambda alpha, delta lambda beta, chi alpha beta, where chi alpha beta is d alpha psi d beta psi, where by d alpha, just to shorten notation, I mean d by d lambda alpha. So you even don't need to think about vector spaces because you always change lambda in some direction. So it's actually, you can say that let me just, this is equivalent to looking into some particular components of this. Or you can say that psi of lambda plus delta lambda will be delta lambda alpha times d alpha of psi. And then you automatically get this type of sums. So it's very easy to derive. But this is, yeah, and here I have to add one thing. It's going to be a connected correlation function, which actually means that I have this overlap, d alpha psi, d beta psi, minus d alpha psi, 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 d beta psi. So when I urge you to do this derivation yourself, but the reason why this connected sum appears is that when you consider perturbation theory, you always have a sum of excited states. So you exclude, say, psi. So if you do this, it's like in when we were computing correction to the energy. Remember, we were excluding energy 0. We were summing over all states except 0. So, and the same will appear in this overlap. So we have to consider overlap. So if you want, you introduce here intermediate states, and you exclude state n equals to 0. That's how it's done. But this is nothing but connected correlation function of this gauge potential, right? Because we define d by d beta up to I is gauge potential, but I have 1a here, 1a here, so one comes with plus I, one with minus I, so I cancels. And then what I see is this geometric tensor, which defines the distance between my wave function, is nothing but the covariance of this gauge potential. So in this geometric tensor is a very important object, which I'll discuss in some detail, but not full. So one thing is that in literature, well, as we'll see from here, of course, this is completely symmetric under change of alpha and beta, so it means only symmetric part of chi enters the distance. So, and I will introduce it. So, symmetric part is called Fubini study metric, and imaginary part is actually Berry curvature, which you probably all of you heard about this. So, there is actually interesting story behind this gauge potential. In 1980, it was not so long ago. In this paper, Provost and Vallée, you can have a look. So they introduced this object. They said it's very nice, but they kind of literally said that, of course, in real experiments, one measures not distances between wave functions, but some physical properties like absorption, emission, so on. So therefore, this is an interesting mathematical object, but it has probably no relevance in physical world. And 4 years later, in 1984, there was a famous paper by Berry, where he introduced his Berry curvature. And as we know, like many phenomena, very interesting phenomena, are defined by Berry curvature, including this quantum Hall and so on. And this is nothing as antisymmetric part of this potential. So I guess one lesson you learn, if you see beautiful object with nice properties, most likely it will show up in some experiment. Anyway, so let me, I'm not really expert in information geometry, so I'm not going to discuss anything beyond the picture. But this object is very often called information geometric tensor. And there is a big community of information geometry who really studies this and uses it. And it will show up actually in adiabatic transport and speed limits and all like these properties. But let me just qualitatively say why this object is related to this information geometry. So sort of the idea is that suppose you have some loosely speaking psi as a function of lambda. Of course, it's a multidimensional object, but this is sort of a way to say that my wave function depends on lambda. And then suppose I measure psi, whatever it means, ask information geometry guys, with some accuracy delta psi. Just say, define it. And then from measuring psi, you're trying to figure out what lambda is. So you measure wave function of a spin, and from this you're trying to find out what the magnetic field is. And then, of course, you will see that your uncertainty in delta psi will translate into uncertainty in measuring, I guess it's opposite. So this is uncertainty in delta psi, and this is uncertainty in delta lambda. And you see, if I have very flat curve, then small uncertainty in delta psi will result in huge uncertainty in lambda. I cannot really tell you precisely what lambda is. And it makes sense. If my wave function is not sensitive to this parameter lambda, kind of measuring wave function, I know very little about lambda. On the other hand, if my psi, if I have, for example, spin in a magnetic field with a very small gap, then my wave function is extremely strong function of this magnetic field. And even if I have some uncertainty in measuring delta psi, I have very small uncertainty in lambda. So, and then you can ask what characterizes this. And then from this picture you see, well, it's derivative of psi with respect to lambda. It has to be second derivative. It's linear, I can always subtract. And this is how it appears in information geometry. So this object also tells you how much you can infer about lambda by measuring psi. And that's why it's called quantum information geometric tensor. Okay. So I'll maybe say a few words about this geometric tensor. You can read more, and I guess I'll show some examples how you can define geometry of phases or maybe phase transitions. I think it's very interesting, but not very well developed. So yeah, as I said, you can define symmetric part of chi, like 1/2 chi alpha beta plus chi beta alpha, which is nothing but symmetric covariance of this gauge potential A alpha, A beta plus A beta, A alpha. And I'll try to convince you this really defines the mass in the classical limit. So mass, which we were computing before, is really related to distance between wave functions. And then we can also define an antisymmetric part. And by convention, it's defined with I in the commutator, well, because it's real. And this is called Berry curvature. Well, it's clear why I have Hermitian operator A, Hermitian operator B. Commutator of two Hermitian operators is anti-Hermitian. So I multiply by I, then I get a real object. It's expectation value of Hermitian operator. So I guess many of you saw Berry curvature in this form, but mostly you probably saw it in this form. D alpha A beta here, not curly, it's a Berry connection minus D beta A alpha. And this is really easy to see that it's the same. Because if I use definition, this later definition, it's like d alpha psi d beta psi minus d beta psi d alpha psi. But then you see when I differentiate this, I will get double derivative here and double derivative here, which will cancel. And then I will get single derivative here, single derivative here. But it's precisely like gauge potential acting on left, A alpha, A beta acting on right, minus opposite. And that's exactly the commutator. So in this sense, there is like a general analogy that my Berry connection is like a vector potential. Berry curvature is like magnetic field because it's a curl of vector potential. And flux, which is integral of the Berry connection, plays the role of magnetic flux. Sorry, phase plays the role of magnetic flux. So probably many of you heard about this topological phases, and I'm really not expert there. I'm not going to discuss them that much. But let me just say in 2 words how we can get topological invariance from this Berry curvature, and then I will try. I will show how it appears in dynamical response, and this is sort of a general reason why quantum response, dynamical response is geometric, not just in quantum Hall. So let's assume that we have some closed manifold of parameters, which usually in literature you'll see some momenta in 2-dimensional lattice, kx, ky. They don't have to be momenta, and I will show example where they're not components of magnetic field. But it's important that I have a closed manifold. So you can think about I have a spin system and I have magnetic field which lives on a sphere. Then I can define a Berry phase in 2 ways. So as I said, it's an integral. So I can define Berry phase, again up to a sign. It's an integral of the Berry connection over this contour. But then I can use a Stokes theorem, which tells you that it's an integral over the area, I don't know, say C and D, over area C, F alpha, F phi theta, D phi, D theta. Right. On the other hand, I can define exactly same phase as minus integral over D. And remember, in Stokes theorem, it has to be, surface has to be oriented. So if C is oriented up, means D is oriented down. So I have to change sign. So it's minus integral over D, F phi theta, D phi, D theta. But it's the same phase. But as we know from physics, phase can be defined up to 2 pi, because if I get a different result for the phase modulo 2 pi, it's not important. It's a phase of wave function. So it actually means I could call it phi c, I can call it phi d. Phi c minus phi d has to be 2 pi n, where n is an integer. And this is nothing but the closed integral of phi theta, d phi, d theta. So, and I guess most of you know about this. So this is what's known as Chern number, first Chern number. And it really comes from this Berry curvature, which really comes from gauge potential and so on. So you probably also heard about another set of geometric invariants related to Euler characteristics, so which are more interesting. I won't have time to talk about them, but those are related to G, to real part, to the metric. You can define curvature formally through E, and you know that if you integrate over the surface, you'll basically get an integer, which is given to number of holes, and so on. And this way of characterizing phases was not really used, so I will show you next time, I guess, some examples, but I think in general it's a very interesting direction. I don't know how much time I have. Do I have? I can show like maybe 10 minutes. Okay, so let me see what I want to discuss. So I can let me discuss, it's probably boring, it's a Wikipedia example, but let me still go through this. So I will give you here how we can get geometry of a spin 1/2 in magnetic field, and then I show you more complicated examples tomorrow. So I defined geometric tensor, and let me just try to argue that this makes sense. So let me consider literally this problem. So I have a spin in magnetic field. So it's minus, my Hamiltonian is minus h cosine theta sigma z. It's the one which I introduced before. Sine theta cosine phi sigma x minus h sine theta sine phi sigma y. So now my theta and phi are parameters which characterize angles of magnetic field, but they form a closed manifold. So it's good. I can define various topological numbers, and I can define a metric. So now I can compute my metric tensor, right? So my ground state, let me do it for the ground state. My ground state, G, is cosine theta over 2 sine theta over 2 e to the, I think, minus I phi, but could be plus I phi. So let me just try to compute this geometric tensor for this spin 1/2 and see what it is. Right? Well, for the Berry curvature, I just need to compute expectation value of my gauge potential, right? And or I can just compute I, G, G theta, G. So this will be my A theta. But this you might check immediately is 0. You can just see it. When you differentiate cosine and sine, you'll get minus sine and cosine. And when you multiply it by G, you'll get minus sine times cosine plus cosine times sine. This is 0. And there is a general statement that if you have a real eigenstate, then Berry connection is always 0. And the fact that you rotate by phi is not really changing it, because I can change my x-axis along phi. So now if I compute A phi, then I will get non-zero. I will get I cosine theta over 2 sine theta over 2 e to the minus I phi. And here I get derivative of G. It will be minus I sine theta over 2 e to the minus I phi, right? Sorry, I forgot. Yeah, I think that's OK. So I will get sine squared theta over 2. And now if I want to compute f theta phi, this is the same as d theta a phi minus d phi a theta. This is equal to sine theta over 2 cosine theta over 2, which is 1/2 sine theta, if I did mess up. So I already computed part of my geometric tensor. It's a Berry curvature. And this is really a Wikipedia example. I just illustrate that you can get Chern number, which is an integer. So as I said, you integrate over a closed surface, so d theta d phi over all sphere, f theta phi, which is the same as 1/2 integral of d theta d phi sine theta, which is nothing but the full spherical angle for pi. So it's the same as 2 pi. So Chern number is 2 pi times an integer, so this integer is 1 in this case. If you consider excited state, you will get a Chern number which is -1. Now in this similar way, you can compute g phi phi, which is d phi g d phi g, and g theta theta, which is d theta g. Yeah, sorry for notation. So this g means ground state. It's not a metric, but I'm also tired. Connected. So if you compute derivative of this with respect to theta, you will get 1/2 sine minus cosine, and another derivative with respect to theta, you'll get another 1/2 sine minus cosine. So you multiply them together, sine squared plus cosine squared will give you 1, and 1/2 squared will give you 1/4. And I'm a little bit fast, but this is what it is. If you compute g phi connected, well, you will get overlap of two derivatives with respect to phi's. And this is just sine squared of theta over 2, right? So this comes from the fact that when you differentiate with respect to phi, this is 0. This is just I, minus I. But then you multiply by another derivative, so I cancels, and I get sine squared over 2. But it's connected, so I need to subtract overlap with g, which is Berry connection, which I already computed. So square of this, I will get sine to the 4th of theta over 2. If I'm too fast, just check it. So this is the same as sine squared theta over 2 cosine squared theta over 2, which is the same as 1/4 sine squared theta. So now I can say that if I define infinitesimal distance between wave function, delta squared, it will be equal to 1/4 times delta theta squared plus 1/4 sine squared theta times delta phi squared. And I see that this metric of my ground state manifold is nothing but a metric of a sphere with the radius 1/2. So remember, if you consider a sphere of radius r, and you consider distance between points on the sphere, you'll get r squared d theta squared plus sine squared r squared d phi squared. So in a way, in this simple problem, you get what you expect. So the Berry curvature just tells you, well, it tells you about the spin. And it's opposite for the ground and for the excited state. And the metric is actually the same for the ground and excited state. It's the metric of the sphere. And you can do this calculation for arbitrary spin S, and you will see that in this case, geometry of this spin is equivalent to geometry of a sphere where radius is just S over 2.
Sorry, I'm confused. What is Berry curvature and what's Berry connection?
So Berry connection is expectation value of the gauge potential. So Berry connection, if you want, is like energy or expectation value of Berry connection. And Berry curvature is a derivative of this Berry connection, this antisymmetric derivative. Or its expectation value of commutator of gauge potentials. So it has two indices. So it's expectation value of commutator of, say, A theta and A phi as operators. But it's also the same as derivative of Berry connections. It's equivalent. Expectation value of a commutator is the same as derivative. So the fact that we are getting geometry of the sphere is, of course, kind of trivial. In this example, all directions of magnetic field are completely equivalent. So it actually means that if I change my parameters, theta and phi, my wave functions should change in completely symmetric way. So I cannot get anything but the sphere. But you can imagine that in the more complicated examples, and I'll show some, the story is different. Like, for example, near the phase transition, my wave function will change very, very quickly. And then my metric tensor will blow up. So I'll show you some examples. So phase transitions can be characterized by singularities in the metric. And same with non-adiabatic response. So you can sort of already see the connection. So the metric tensor, in some sense, is a norm of this gauge potential. It's how big this gauge potential is. But we saw that this is the object which enters a Galilean transformation. So if you go to the moving frame, this is the object which defines how much I excite the system. So you already see connection with qualitative level. So if my wave function changes slowly, it means my norm of the gauge potential is small. It actually means that I can be very adiabatic. So my correction due to moving frame transformation is tiny. On the other hand, if my metric is big, so I change very rapidly, if I change the parameter of the Hamiltonian, then it's very hard to be adiabatic. All right, so I think it was enough for today. At least it was enough for me.